So this one is one of the questions from quiz 345. Is it right?
Yeah, it was.
3,
It was
4,
number 3A.
3A. Thank you. So I will just leave it here. Okay. Besides number 26 and 30, is there other question you want me to go over from this 7.3? Choose 3 more questions. Or maybe 4, doesn't matter. We did only number 6 and 8 last time.
Could you do number 15?
Number 15, number 38, number 15. Maybe one more.
Can you do number 28?
28. 28. Okay, 28 here instead. Somebody just canceled that 38. Okay, remind me that the one who's that Robert. Yeah, remind me when I do number 7, section 7.4. Okay. Let's do number 12 also then. Eh? I have something coming in. Yeah, number 12 or number 10. Which one do I like? Maybe I do number 12. Number 12. Number 12, the question is integral du over u square root of 5 minus u squared. Then I set my u equals to radical 5, what, sine? Yeah, radical 5 sine theta. So du equals to radical 5 cosine theta d theta. Now, of course, then 5 minus u squared, 5 minus u squared equals to 5 minus 5 sine squared theta. I factor the 5. I factor the 5. I get cosine squared from 1 minus sine squared. Right? So the square root of that will be square root of 5 minus u squared equals to square root of 5 times cosine theta. Okay, supposed to be in absolute, but I will just ignore it for now. Now then, going back to that integral, that's the setup though. Okay, don't skip the setup, don't even rush it. Okay, just make sure that if you can do it fast, but if I were you, I will not skip it. Okay, I have seen people making silly mistakes simply because they didn't do it right here, and then they waste so much time after that. And then they say, Thomas, your test is so hard. No, it's easy. It's because it's so easy that you skip steps and then you mess up here and there. And then you still blame it on me. Duh. Okay. To be more precise, this section is tedious. Okay. Is it hard? Don't know, but not writing things properly basically make it hard for you. So not a good idea. Okay, so write them properly. So this is the u becomes radical 5 sine theta. And then the square root of 5 minus u squared is square root of 5 cosine theta. Gada-bum, gada-boom, 1 over radical 5 goes out, 1 of the radical 5 cancels, then I have cosecant, cosecant theta d theta, like this. The 1 of the radical 5 cancels, right? And cosine theta also cancels, right? So Sine theta on the denominator becomes cosecant theta. However, the integral of cosecant theta is, I wonder if you remember, I honestly don't remember. Cosecant minus cotangent. Is it right? Okay, nobody say anything. Well, anyway, now then I need to put it back in terms of u. So look back into my triangle. Sine theta is u over radical 5. So if this is theta, this is u, this is radical 5, this is square root of 5 minus u squared. Okay, so cosecant theta is the reciprocal of sine. That's radical 5 over u. Natural log of radical 5 over u. Cotangent theta is, if you follow the triangle again, let me write the triangle here. The triangle here, this is u, this is radical 5, this is square root of 5 minus u squared for this theta here. Okay, so the cotangent is radical 5 minus u squared over u plus constant. Put them together, this will be 1 over radical 5 natural log of radical 5 minus radical 5 minus u squared over u plus constant. By the way, yes, that's number 12. Any question?
Could you take out the ln u, like minus ln u?
Yes, you can. Yes, you can. So this is 1 over radical 5 natural log of the square root of 5 minus square root of 5 minus u squared minus 1 over radical 5 natural log of u plus constant with absolute u though. Okay, so the answer is yes, you can.
Would you want us to write it like that, or are you okay leaving it like the
Either one is okay. Either one is okay. Yeah, you will see that if the u were a constant, then you will want to do it that way. Because this becomes constant, right? Okay, if u
Right.
were constant, this is constant, and this constant here absorbed with that constant, making a new constant.
Right. I mean, yeah, I noticed that in your lectures, like you would take that negative ln of whatever constant, and it would just become the new constant.
Yes, yes. Yeah.
Okay.
For this number 12, I suspect that it is doable using another method. Let me try number 12 redone. Hopefully we get the same answer, but I'm not sure though. Okay, I'm not sure. This is where group study is actually very helpful. So somebody may think this way, okay, I have du here. This is u square root of 5 minus u squared. Okay, and I want to do substitution, like let's say, no, I don't want to use v. Let's use a. No, it's not good either. Can you suggest a variable for me? I use x then. X equals to 5 minus u squared. So dx equals to negative 2u du. But before I really work that out that way, I will modify this a little bit first. Integral u du over u squared, square root of 5 minus u squared. Basically, I multiply the top and the bottom by u. Okay, so what happened is I end up with integral u du is negative 1/2 dx. U squared is 5 minus x, right? And then this is square root of x. Now you will see later on, this is actually doable using some other technique. Okay, something we will see in 7.4, I think. This is integration by parts. I mean, partial fraction decomposition. Yeah. May proceed with partial fraction decomposition. Something we see in section 7.4. Maybe. I'm not sure. I'm not sure. But at least now you see we have polynomial. Okay?
Why is u 5 minus x? Am I missing something?
Not u equals to 5 minus x. It's u squared right now. I multiply the top and the bottom by u.
Right.
So
I guess where did you get the parentheses 5 minus x? Isn't that the substitute for u?
Substitute u squared. Substitute u squared. So x equals to 5 minus u means u squared equals to 5 minus x.
Oh, okay.
Right?
Okay, yeah.
Now that's for number 12. I cannot finish it because we have not done partial fraction decomposition. Okay. Let's see, number 15. Number 15. Integral from 0 to a of x squared square root of a squared minus x squared dx. So my substitution will be x equals to a sine theta. Is it right? So dx is a cosine theta d theta. While a squared minus x squared will be a squared cosine squared theta. Let me go slower, just in case you wonder why. Because that's equals to a squared minus a squared sine squared theta. But you factor the a squared, right? And you get 1 minus sine squared theta. That's how we get that cosine squared theta inside. Therefore, square root of a squared minus x squared is equal to a cosine theta. Again, it's supposed to be in absolute. It's supposed to be in absolute. However, we don't need that absolute. We don't need that absolute because of the following. Because the following. When x equals to 0, what is theta? Sine theta equals to 0. So theta equals to 0. When the x equals to a, sine theta equals to 1. So theta is pi over 2.
Wait, how did you get that?
Huh? Sine theta equals to 1. So the angle must be pi over 2. I get annoyed with this very, very loud voice. Darlene,
Yeah.
I think your volume is way too high. Your speaker volume.
Oh, can you hear my son's TV? That's
no, it's
sorry.
like the white noise. They are like really loud.
Oh, is it me? I'm sorry. I don't know.
Maybe you, maybe I'm not. I don't know. It's just like really loud, really loud. Yeah, but right now it's good. Right now it's good.
Okay. Well, I put the volume down, so I don't know if that will help.
Maybe earlier is over. Earlier is kind of like really, really high.
Oh, okay. Yeah. So how did you get A equals? So did you put? Wait, that's what I'm confused.
The limit of integration.
Yeah, I understand that, but how does that equal to 1?
A over A.
Oh, I see. I mean, I figured that seemed like such a simple thing, but I just wanted to make sure that was it.
Yeah, over A. So now the integral becomes from 0 to pi over 2. Now x squared is a squared sine squared theta. Okay, now square root of that is now a cosine theta. And the dx is a cosine theta d theta. Okay, so things to pay attention. The limit of integration. You need, once you do substitution, limit of integration should be changed right away. Okay, I mentioned it a couple of times already. Okay, to the point that the next time you do that, I will really ask who was your calculus 1 teacher. Okay, and if you don't tell me, I will find out and I will yell at that teacher in the math department meeting. They mess you up. Okay, it's discipline though. It's discipline. No, I didn't teach you Calc 1. I have never taught Calculus 1 in the last 20 years. So
well,
I know.
Maybe it's your fault, Thomas. You should have taught Calculus 1.
Nah. At least don't blame it on me. Maybe it's time for me. No, I don't want to. Okay, Calculus 1 is the only class like I don't want to teach. Just like, oh no. You don't want to take Calc 2? Too bad, man. You have to. That's why you're here, right? Now, let me simplify this. So this is 0 to pi over 2. I take the a to the 4th out. So I have sine squared theta cosine squared theta d theta. Now then we need to look back to what we did in 7.2. In 7.2 we did trigonometric integral, right? What happened if sine and cosine both even exponent? And we use double angle formula. Okay, there are two ways to do this. Let me do it this way. I will write it as sine theta cosine theta being square d theta. How about that? This is only one way though. This is only one way. And then we know that sine theta cosine theta is half of sine 2 theta. Let me continue up here. So this is equals to a to the 4th over 4 integral from 0 to pi over 2 of sine squared 2 theta d theta. Still, I need to do half angle, actually double angle. So this is a to the 4th over 4 integral from 0 to pi over 2 1 minus cosine 4 theta over 2 d theta. Okay, so this is equal to a to the 4th over 8
Hey,
integral.
Thomas?
Yes, huh?
Sorry to interrupt. I have a quick question.
Uh-huh.
Could you run over like how you know you have to do the half angle formula? Is it because it's in the
Double
form
angle.
or the
Double
double
angle.
angle? Sorry.
Because I don't have odd exponent to help me with the substitution. Suppose if I have cosine cube, right? Then I will make it cosine squared times cosine and do u equals to sine,
Oh, so your goal right now is to
right? But the thing is, because these are both evens, then I cannot really do it. Then I will, what I do is I make it into basically double angle instead.
okay.
So what happened is when I do double angle, I still have square.
Right.
Then I do double of that angle again.
So gotcha. Okay, thank you.
Okay. And then this is one integral from 0 to pi over 2, 1 minus cosine 4 theta d theta. Okay, and this will be a to the 4th. I really want to skip steps. This is integral of that one is theta, integral of the cosine is -1 for sine for theta from 0 to pi over 2, right? So this is a to the 4th over 8 times pi over 2. So a to the 4th pi over 16. Now when I plug in pi over 2 here, multiply by 4, I get 2 pi. Now sine 2 pi is 0. Sine 0 also 0. Now, if you happen to see that a lot earlier, you can save some steps. And you can just kill it before it comes out from the absolute, comes out from the integral. Here, you can kill it here actually. Why? Because integral from 0 to pi over 2 of cosine 4 theta d theta, some trigonometry background. Cosine theta have period 2 pi. The period is 2 pi. How about cosine 4 theta? What is the period? Divided by 4. Right? In other words, cosine 4 theta is already have one period in this integral, so the total area must be 0. Right? The area here is the same to the area here. The area here is the same to the area there. If you can imagine the graph, okay. If not, then you do it long way. Okay, but if you didn't catch it there, then eventually we'll see, oh, that's they cancel each other anyway. Okay, that's for number 15. What's next? Number 26. Number 26, integral of x squared over 3 plus 4x minus 4x squared to the power of 1/2 dx. Let's focus on that denominator first. That's 3 plus 4x minus 4x squared. 3/2. Oh, thank you. Not 1/2, 3/2.
Oh, this is the one where you complete the square.
That's right. That's right. That's right.
Yeah,
So,
I saw that you did this one in your lecture.
oh yeah. Okay, so do you want me to go on? This is 4
Yeah, that's fine. You can
minus,
still do it.
4 minus 1 plus 4x minus 4x squared. So I can rewrite it as which way? Okay, 4 minus parenthesis 4x squared minus 4x plus 1. So basically, I group these three together and I factor the negative. I factor the negative and I rearrange at the same time. Okay, so this is now 2 minus 2x minus 1 squared. So this is y2. It's
Wait.
4.
Yeah, I was gonna say, why
Should be
did you
4.
put the?
Should be 4 there. I don't know where I stole that 2 though. So this is 4 minus 2x minus 1 squared to the power of 3/2 dx. Okay. Now then, what kind of substitution should we do here? Call this
It was
RU.
2.
So 2 what?
Wasn't it 2 sine theta?
2 sine theta. Okay. To replace what?
2x minus 1.
Okay, good. So 2 dx equals to 2 cosine theta d theta. Is that right? Or in other words, dx is equal to cosine theta d theta. Now, how about x squared? So 2x equals to 1 plus 2 sine theta. So x is 1/2 of that. Because I need to substitute the x on the top also, right? Okay, so the x we know we need to substitute the x by this. Okay, the dx will later on be substituted by this. Now, how about that ugly guy at the bottom? It's so fugly. So 4 minus 2x minus 1 being squared will be 4 minus 4 sine squared theta, that is 4 cosine squared theta. So the square root of that, will be 2 cosine theta. Now the cube of that will be the power of 3. That's the power of 3/2, right? This is 8 cosine cube theta. See, it takes much longer for me to set it up properly, just so that I can substitute correctly. Okay, now, then I do substitution. X squared becomes something over 4. And then 1 plus 2 sine theta squared over, at the bottom we have 8 cosine cube theta, and the dx is cosine theta d theta. So that's 1 over 32 integral 1 plus 2 sine theta squared over cosine squared theta d theta. Now what?
Do you would it be a good idea to FOIL the top, the numerator?
That's what I have in mind too. 1/32 integral of 1 plus 4 sine theta plus sine square theta over cosine square theta d theta. So that is equal to 1/32 integral of secant square theta plus 4 secant tangent plus tangent square theta d theta.
Did you basically put like the cosine square theta under each one?
Yeah, basically. So
Oh,
1 over cosine square theta is secant square, right? And then
Yeah.
this will come secant tangent, and this is tangent square.
Okay.
Now, integral of secant squared is tangent, as I remember. Okay, but how about integral of tangent squared? You know what? Let me just massage that right away. Tangent squared is secant squared minus 1. So this is 2 secant squared theta minus 1. What do you think? It's because tangent squared theta equals to secant squared theta minus 1. Okay, now integral of 2 secant squared theta is 2 times tangent theta minus theta plus, this is for secant. Is it right? Derivative of tangent is secant squared. Derivative of secant is secant tangent. Now I have to put this back though. Oh man, this is painful. Okay, let's look back here. This is 2x minus 1 over 2 is sine x. The substitution we used earlier is 2x minus 1 equals to 2 sine theta, right? In other words, sine theta equals to 2x minus 1 over 2. If we draw the triangle, this is theta, this is 2x minus 1, and this is 2, such that this is square root of 4 minus 2x minus 1 squared. But we knew that this is square root of 3 plus 4x minus 4x squared.
So basically, every time we use like the trig functions, we always have to
Trig substitution.
okay. The trig substitution. Every time we use that, we always have to make sure to get the
go back to the x.
Their angles.
Oh,
okay.
Unless you have a definite integral, then you don't have to anymore. This is square root of 3 plus 4x minus 4x squared minus theta. Theta is sine inverse of 2x minus 1 over 2 plus 4 secant. Secant is 8 over square root of 3 plus 4x minus 4x squared plus constant. But the numerator, I think, is the numerator here. Well, they have common denominator here, right? So I can combine the top. Okay, I can combine the top. If I do, I will get 4x plus 6 over square root of 3 plus 4x minus 4x squared minus sine inverse of 2x minus 1 over 2 plus constant. You said that I did it in my lecture. Can you tell me if I get the same answer? Imagine if I get different answer.
You got 5x plus 4 over 16 times the square root of 3 plus
5x.
well, all of that. Yeah, 5x plus 4 over 16 square root of 3 plus 4x minus 4x squared minus the sine inverse of 2x minus 1 divided by 2 plus c. I think it's because
no 1 over 32?
No.
Ooh.
I think it's yeah. I think it's because in the lecture you damn it, you multiplied 1/8 into everything basically. Yeah. Because you got 1/8. Oh wait, hold up. Because yeah, what you did differently was that you took out the 8 and you multiplied it with the 4, the 1/4, and you got 1 over 32. You didn't do that until like the second to last step in your lecture.
Oh yeah. You know what? Let me see. Can you tell me which minute is that?
Oh, okay. Hold on. I don't know. Hold up.
Minute number what?
Okay,
because it is possible that's the one I make mistake, right? Or maybe I make mistake somewhere here and I don't see that.
No, like I said, it's because you distributed or you multiplied 1 or 532 into everything. Okay, hold up. Let me see if I can find it. Okay, it is hour 26:38 seconds. This is when you're starting to put it or take it apart so that you can start substituting.
Number what?
Oh, sorry.
Minute what?
That is week 4B.
Uh-huh.
Hour 26 with 38 seconds.
26:38. Wait, but that's number.
No, it's 1:26:38. So 1 hour 26:38.
Okay. I look at the 26 instead. I think I know where I make the mistake earlier. My coefficient. Give me a second. I need to stop this. I see that. I make mistake here. Here. This is my mistake. Let me mark it here. I forgot the 4. I forgot the 4 there. Okay, fix it. So I have 4 here. So that will be 5 here. Okay, let me do the correction. So this should be 4. This should be 4. So that
Oh,
will
when
be,
when you foiled the 1 plus 2 sine theta.
yeah, so it's supposed to be 1 plus 4 sine theta plus 4 sine squared theta. So that will be
Okay.
5 here, and this will be 4. Okay, at least that's not too hard to fix. This will be 5 here. This will be 4 here. So instead of 2, now I get 5. And I have 4 here. I have 4 here. Mark it. So this will be instead of, see, good thing I show my work properly, right? Otherwise it will be so hard to fix. So this will be 10x plus 3. That will be 10x plus 3. So if I distribute the 1 over 32, no, I don't need to actually, just leave it like that. So 1 over, I fix it. So this is 1 over 32, 10x plus 3 over square root of 3 plus 4x minus 4x squared minus 4 sine inverse of 2x minus 1 over 2 plus constant. Now if I distribute that 1 over 32, then I will get that 1/8 sine inverse. Let's see.
Wait, but in the lecture was the lecture, it was just minus sine inverse of 2x minus 1 over 2 plus c. Even unless I'm tripping. Oh, wait a minute. Oh, okay, yeah, I don't know.
Should be 1/4. I forgot to distribute that 1/8 in that question.
I was just gonna tell you that right now.
Yeah, let me pause this, enlarge this, and share that with you. So I make mistake on this one here. I forgot to distribute the 1/8 here, right? And then this is supposed to be 1/4. Oh, hold on. No, it's supposed to be -1. That's right. -1. I wonder where I get this though. Tangent. No, it's not. So something not right with this. Something not right with this. The way I define how, I wonder how I define my. So not something not right with this. Something not right with this. The tangent theta should be 2x minus 1 over these. So it should be 2x minus 1 here. In my opinion, the one I just wrote is the correct one. But it's more about, I prefer to say that show your work so that you can find your own mistake. Right? Okay. So see if I make mistake here. Okay, I was too fast on that. And then notice that I actually skip steps a little bit here. That's 4 secant minus 4. Okay. That's 2. See, earlier my tangent, so I wrote 2x over, right? Supposed to be 2 over this in that video. Notice that I substitute my tangent with 2x over something, supposed to be just 2 over something. This is supposed to be 2x minus 1 here. It's supposed to be 2x minus 1. This is correct. This is 2x minus 1 supposed to be. So what you can do if you really want to, I do it then. I do it. So let me do correction over this. Let me do correction over this, but I need to do screenshot though. Oh. I want to do screenshot over that one. And put it back into my note. Okay, let's do the fixing. So that's supposed to be 2x minus 1 here, right? And this one here is supposed to be 4. Now then, if we do the boom thingy, do we get what we need? This is 10x minus 5 over 32 blah plus what's that, multiplied by 4 multiplied by 4 on the top. That's 8 over 32 blah minus 4 sine inverse 2x minus 1 over 2 plus constant. Now then when I put these together, I will get 10x plus 3 over 32 blah. Right? Okay, and then the one here, remember I said that I forgot to distribute the 1/8. Okay, I distribute the 1/8. I forgot to distribute the 1/8, which I will get here if I distribute this 1 over 32 by 4. That's my 1/8. Why I suddenly feel like I'm now an accountant. I basically need to reconcile 2 works, each of them with mistakes, but they make different mistakes. Okay, that's for number what? Number 26? Number 28. Number 28, integral. Did I do this in my lecture? I don't think so. X squared plus 1 big over parentheses x squared minus 2x plus 2 being squared dx. The guy at the bottom, that's x squared minus 2x plus 1 plus 1. That's x minus 1 squared plus 1. So what substitution should I use? So x minus 1 equals to tangent theta. Right? So dx equals to secant squared theta d theta. Right? So I can rewrite this now. For now, I will rewrite this x squared plus 1 over over x minus 1 squared plus 1 being squared dx. Okay, so x minus 1 equals to tangent x, then x will be tangent theta plus 1. Okay, and then how about x squared, x minus 1 squared plus 1, x minus 1 squared plus 1 will be tangent squared theta plus 1 times secant squared theta. Okay, so we can do substitution now. This is integral tangent theta plus 1 being squared, that's my x squared, plus 1 big over, on the denominator, that's secant squared theta being squared, times the dx is secant squared theta d theta. Then simplify a little bit, I get tangent theta plus 1 being squared plus 1 over secant squared theta d theta. How to do this one? Let me fold the top. So that's tangent squared theta plus 2 tangent theta plus 1 plus 1 over secant squared theta d theta. Tangent squared plus 1 give me secant squared. Okay, so one of them nice, secant squared theta plus 2 tangent theta plus 1 over secant squared theta d theta. Is it okay so far? This guy together with this give me this. But then, let me do one more step here. This will integral of 1 plus, I get this. But I wonder what's the middle. Oh, 2 sine cosine. Oh, nice. Tangent theta, 2 tangent theta over secant squared theta equals to 2 times sine over cosine. That's 2 tangent theta. And then secant squared theta will be cosine squared theta on the top. Right? So one of the cosine cancel, that's what I get. Then let me continue on the right hand side here. That's equal to theta plus, you know what, I will integrate it later. Oh, integral of 1 plus secant 2 or sine 2 theta plus 1 plus cosine 2 theta over 2 d theta. The constant add up together, the 3 half, 3 theta over 2 minus cosine 2 theta over 2 plus sine 4 theta, sine 2 theta over 4 plus constant. Now the thing is, I don't like that cosine 2 theta and sine 2 theta. Dang it. Because I need to change it back to x, right? Why do you write this kind of question? Okay, what did we have? Let me rewrite this into sine cosine 3 theta over 2 minus. This is 2 cosine squared theta minus 1 over 2 plus 2 sine theta cosine theta over 4 plus constant. What is my tangent again? X minus 1 is equal to 10. So x minus 1 over 1, this is square root of x squared minus 2x plus 2. Tangent theta equals to x minus 1. So theta will be tangent inverse of x minus 1 over 2 minus cosine squared theta. Cosine squared theta is 1 over x squared minus 2x plus 2. I want to say that this plus 1/2 here will combine with our c later on. Okay. And then plus 1/2 sine theta is what? X minus 1 over 1. I'm sorry. No, that's not true. X minus 1 over this guy. And the cosine is 1 plus the constant. Okay, then the final answer will be 3 over 2 tangent inverse of x minus 1 plus x minus 2 over x squared minus 2x plus 2 plus constant. Yeah, it's really about how to put it back. It's really
Thomas,
about
how did you get 3 over 2 for theta?
That's from this one plus that 1/2. That's 3/2, right? And then you integrate respect to theta, then you get extra theta.
Oh, I see. Okay. Oh, okay. I was a little confused. Okay. Oh, so basically what you did, we just took the 1/2 out of cosine 2 theta, right?
Mhm.
Kind of.
So forth. The thing is, with that double angle, I need to bring it back to single angle so that I can refer back to that triangle. Number 30. Number 30, integral from 0 to pi over 2 of cosine t over square root of 1 plus sine square p dt. Do you want to do u sub first? Let's do u sub first. So u equals to sine t. So du equals to cosine t dt. And when the t is 0, u0 is sine 0, that's 0. U pi over 2, that's sine pi over 2, that's 1. So my integral now becomes integral from 0 to 1 du over square root of 1 plus u squared. Now then, we say let u equals to tangent theta, which if you think about it, you can, since the beginning, you can do this substitution. Sine t equals to tangent theta. Okay, so cosine t dt equals to secant squared theta d theta. Okay, but instead I did it in 2 substitutions. That's also fine. That's okay. Instead of doing it all at once, I break it up into 2 steps. So du will be secant squared theta d theta. 1 plus u squared equals to 1 plus tangent squared theta, which is secant squared theta. So the square root of that will be secant theta. How about the u1, and when u equals to 0, theta equals to 0. When u equals to 1, tangent theta equals to 1 means theta is pi over 4. Like tangent pi over 4 is 1. So now my integration becomes integral from 0 to pi over 4 of secant squared theta d theta. That's for the du, and then on the denominator, that's secant theta. That's equals to integral from 0 to pi over 4 of secant theta d theta. Oh, integral secant theta is what? 1 times. That's natural log of pi. Secant pi over 4 is 25. That's 1 minus natural log of secant 0 is 1. So that's just so this is natural log of radical 2 plus 1. Okay, I basically have answered your question. Okay, in the next half an hour, I would like us to take a look. If you have your textbook, please open together with me at the far back of the book. Table of integrals. Table of integrals. Let's say question. You see that table of integrals number 16, for example. Look at your table of integral very far at the back of the book. Like the second page or third page from the cover. Number 16, try to match with me. Number 16, you will see integral of du over square root of a squared minus u squared. Do you see that? Number 16, that's the one. Number 17, we get integral of du over a squared plus u squared plus tangent inverse u over a plus constant. I think it's with 1 over a here. We have 1 over at the top. At the front. Number 18, we have du integral of u over u square root of u squared minus a squared equals to 1 over a secant inverse of u over a plus constant. Number 19 and 20, we cannot do yet. Need section 7.4. In the past, I asked students to prove some of those number 21 to number 46. I asked students to prove some of those. Okay, because we have not done 7.4, then there are some questions, of course, here that we cannot prove yet. But let's try, for example, number 30. Number 30. Now, this is not number 30. No, I cannot. This is reference page. Reference page 6. Now, number 30, formula number 30 is on reference page 7. Okay, the question, the integral is integral square root of a squared minus u squared du equals to u over 2 square root of a squared minus u squared plus a squared over 2 sine inverse of u over 2, u over a plus constant. The question is, can you prove it? Start from left-hand side. Can you go to the right-hand side? So prove integral of square root of a squared minus u squared du. Can you prove that that's equals to what we have on the right-hand side? I think this one is doable already with the technique we have. Okay. So I will use u equals to a sine. What do you think? Okay, so du will be a cosine theta d theta. Furthermore, then a squared minus u squared will be a squared cosine squared theta, such that the square root is a cosine theta. So this is square root. This guy is a cosine theta, and the du, oh, and the du is there. Okay, follow me so far. Now this is equal to, I can factor 2a out, which is like, and then I get cosine squared theta inside the theta. Okay, but 2 cosine squared theta, this is 1 minus cosine 2 theta. Yeah, plus, not minus. 2 theta. Continue. That's equals to a times theta plus sine 2 theta over 2 is constant. So this is a theta plus a sine theta cosine theta plus constant. Well, because sine 2 theta is 2 sine theta cosine theta. So the 2 cancels. Right, now let's look back to our substitution. U over A equals to sine theta. This is theta, this is U, this is A, therefore this is square root of A squared minus U squared. Okay, so theta will be sine inverse of U over A. That's for the theta. Sine theta is U over A. Cosine theta is square root of A squared minus U squared over A. Hmm. I make a very terrible mistake. Who wrote this too?
I was just about to tell you, but I didn't want to stop you.
Oh, there should be A here. So this is A here. This is A squared. Oh, shoot. So this is A squared over 2. That's A squared over 2. This A squared over 2. This is A squared over 4. So over 2 here. So this is A squared over 2. This is A squared over 2 plus constant. Okay, so I fixed them. Then this is A squared over 2 sine inverse U over A plus the A squared cancel. So I get U over 2 square root of A squared minus U squared plus constant. I think that's what we have to prove on the top. Yeah. This guy here is here. And this guy here is here. of course plus constant, right? So this is one of the assignment I asked some students in my previous calculus 2 to do. How about number 32? Oh, I have a message coming in. Which part, by the way? I was so confused about it. Sorry, my mistake earlier. I wrote that 2 instead of A.
I think he was saying he was confused with the 2 as well.
Oh, okay. So yes, it's supposed to be an A. It's not a 2. Now you believe in evolution? Evolution is caused by some crazy calculus 2 instructor. Okay, let me go on. Let's try another one. Make it stop. Let me try another one. Maybe number 41. Number 40.
Thomas, if you make mistakes, it makes me feel better about my mistakes.
No. That's what I say. It's making mistake, especially for this level, is standard. Just do not make technical mistake. You see, my mistake was a typo. Right? My mistake was typo. Okay, so if this is my question and this question is 10 points, I may penalize you 1 or 2 points, maybe 2 points at most. You know. Okay, maybe 2 points at most. Just not technical mistake. The technical mistake is, for example, this one. The following is a very, very bad technical mistake. Integral of x sine x dx. What do you do? Tell me what technique you use to integrate this. Nobody know? Yes, integration by parts. Supposed to, right? Supposed to proceed by integration by parts. But I have students doing this integral of x dx times integral of sine x dx. I have seen this. And they say, oh, this is 1/2 x squared negative cosine x. And to make Thomas happy plus constant. No, it will never make me happy with that kind of, it's not silly mistake. That's a terrible mistake. Okay. Because if this is true, then integral of x squared dx supposed to be equal to 1/4 x to the 4, if that's true. Because, oh, that's integral of x squared is integral of x dx times integral of x dx, right? But no, that's not right, though. That's not right. That's just terribly wrong, right? You see what I mean? That's technical mistake. Okay, that's technical mistake. Like, how do you integrate cosine squared theta? Trust me, I saw this so much that it's just like, how can you end up in my class? The cosine squared theta d theta. So somebody just say, oh, this is 1/3 cosine cube theta is constant. No, that's not true. That's not true. This is true if the integral was cosine squared theta d cosine theta. That's true. But this is not true. Okay? But yeah, don't feel bad if you make a computational mistake or silly mistake like typo here and there. Okay, I still penalize you, just like I need to penalize myself here, but it's not as crucial as If you make technical mistake, basically super silly mistake. Number 41, integral of square root of u squared minus a squared over u du. According to that number 41, this is supposed to be square root of u squared minus a squared minus a times cosine inverse of u over a plus constant. Oh, I'm sorry, I copied the wrong one. A cosine inverse of absolute of a over absolute of u. Plus constant. Ooh. I'm not sure if this is the way we're supposed to do it. If I don't need 7.4 for this, but let's try. Let me show you how I practice with this. When I practice this, I will do this integral square root of u squared over a squared over u du. And then I scroll this up all the way such that I don't know what's the right-hand side supposed to be. Like this. So cover the answer and try to adventure yourself. That's how you practice. How do I substitute my u? U squared at the front to subtract. That's a secant, right? So du will be a tangent square. Huh? No, not tangent square, secant tangent. The derivative of secant is secant tangent. Right? And then u squared minus a squared will be a squared times secant squared theta minus 1. That's a squared tangent squared theta, such that the square root of u squared minus a squared is a tangent theta. Now with those substitution, then the numerator will be a tangent theta. The denominator is a secant theta. Then the d is a secant theta tangent theta d theta. The yellow. This is the du. This is the u. This is equal to, I think I have a coming up, right? One of the a cancels. The secant cancels, so I have tangent squared theta d theta. Is that right? What is the integral of tangent squared theta? I cannot integrate that, but I can split it into secant squared theta plus minus 1. Such that it becomes a times tangent theta minus theta plus constant. Going up, that's equal to a tangent theta minus a theta plus constant. Now look back to my substitution. Oops, sorry. Put that to my substitution. U over A equals to secant theta. If this is theta, the secant is U over A. So this is square root of U squared minus A squared. A times tangent A theta will be square root of U squared minus A squared over A minus A times theta. Theta is secant inverse of U over A plus constant. So the final answer looks like square root of U squared minus A squared minus A times secant inverse of U over A plus constant. I wonder about this. I think that's the one I have different. Let's take a look. Let's take a look. See, for my part, this part that I have here is secant inverse of U over A. Is that right? Are they the same?
They're the reciprocal of each other, aren't they? Well, except for U has the absolute value.
So let's do it this way first. Theta equals secant theta is U over A, right? Such that the reciprocal cosine theta will be A over U. Okay, so when we say theta equals to secant inverse of U over A, then that's also the same to say theta equals to cosine inverse of A over U. Is it okay? The other issue is, why do they use absolute of U instead of just regular U?
Isn't that where we have to prove that U is greater or equal to something? To 0?
Honestly, I don't know. Honestly, I don't know why it has to use absolute of U on the cosine there, or on the cosine inverse. But the reason that they use absolute of U there in the cosine inverse must be the same reason I supposed to use absolute of U here. You see what I mean?
How would you get that?
Huh? I mean,
How would you get that?
I don't know why they use absolute of U, but if they insist on using absolute of U, then my secant inverse of U over A there supposed to use absolute value also for my U.
Because in the in your lecture for, it was reference page 6, number 24, it was, you know, having to prove that the square root of A squared plus U squared was greater or equal to the square root of U squared, which equal to U. Basically, what you were trying to prove is that the reason why it was in the absolute. Oh wait, never mind.
Yeah, I know what you're talking about. This one.
Yeah,
Natural
but
log
this
of
is kind of going
this one,
backwards,
right?
though. Yeah, that one.
This one, right? Now the thing is U squared plus A squared square root. This is greater equals to square root of u squared. Right? This is greater equals to u, absolute of u, to be more precise. Okay, so even if the u is negative, this guy will be greater than that. Right? Let's say u is -5, right? Now this expression is still positive, so I don't need that absolute value there, but I don't see the reason of doing so in this work that we had just now, except for the following point of view. That in this triangle here, the u cannot be negative. Do you see that?
I would also think it's because the u in the denominator, it well, I'm assuming it shouldn't be 0. Or
But
does that not matter?
absolute of u doesn't mean it cannot be 0.
Oh, I see. Oh, it just basically means it's either sorry, it can't be negative. It's always going to be positive, right?
So I think the reason they put absolute sign there is because of the u here cannot be negative. So even if original u is negative, once you do it in the right triangle, then the hypotenuse cannot be negative. Basically, everything in this right triangle cannot be negative.
Okay.
Right? I think that's the reason. But to be honest with you, they don't do that for other cases. I mean, I randomly picked that question. Okay, I randomly picked that question, but I don't see that issue in other places. Okay, so put it this way. See, this is how I learn. I can confirm that my answer here is actually just another way to write that, except the absolute value. Okay, so if I ask my professor, then I will ask this question: Sir, I got that cosine inverse of a over u, but I'm missing the absolute sign. Can you explain why they have absolute and why I didn't have it? It's like I didn't have it, but where I supposed to put that and why I supposed to put that. That's how I will ask my professor. You know,
would it make more sense if a over u was inside the absolute value and not just u?
The a may be negative and still okay. Yeah, the a may be negative and it's still okay. You know, okay. That's how I study. Well, anyway, is there any more questions you would like me to do from this reference page 6 or 7? Because then your next quiz will be, I pick questions from this reference page and then ask you to prove it. How is it okay for a to be negative but not the u? The thing is, on that right triangle is just to help us figure it out. That's why I want to say that the argument that I used earlier, that the u has to be absolute because it's the length, is actually not, it doesn't really hold. The argument that I need to use absolute for my u here because u is the length does not help, does not hold. Because this triangle here is just to illustrate, you know, just to illustrate how they relate. I know A is also the length, right? Okay, but that's just to illustrate, because if you use right triangle, then you are limiting your U and A has to be positive, but U and A can be in quadrant 2, quadrant 3, quadrant 4. Okay, in other words, what I said earlier, that I'm supposed to use absolute here because it's a right triangle, that's not a good argument. That's not a good argument. Well, it may be good argument in the sense that hypotenuse is always positive, but you see, in quadrant 3, for example, right, the A may be negative, right? The A is negative. This is negative. Oops. Give me a second. Something wrong. Why? Do you see what happened? Seems like my note is not oh, right. Thank you, Thomas. Yeah, my note is restarting. Give me a sec.
Can we take a break?
Yes, I'm about to give you a break. So let me just explain this a little bit. See, yeah. So the coordinate here, let's say this is negative a comma negative b. So this part is still maybe negative. This is negative, but the radius still positive. I think that's the only reason. But refer to this right triangle and say a cannot be a. It's not the purpose of why we draw that right triangle. We just use that right triangle as one representation of the full circle. You want it quadrant 1, 2, 3, 4 all at the same time. Unless we argue that way, that you cannot be negative because it's the radius, right? But I still don't think that's a good argument. I myself don't think that's a good argument.
Could it also be that like looking at that reference page at the very top of the number 39, it says forms involving the square root of u2 minus u squared minus a squared, where a is greater than 0? Could that have something to do with it?
It could be, yeah, it could be something to do with that. The fact that they already restrict the a to be positive. Yeah, but it doesn't make the u has to be positive. Unless, again, we go back and say that u has to be a hypotenuse. Right? Let's say it this way. I can easily get away with the arguments that I'm not saying I'm arguing with you. I'm arguing with myself. Okay, I'm arguing with myself. Thomas, why do I have to use absolute value here? I can easily just say, oh, because that's the radius, right? I mean, that's the hypotenuse, so it has to be positive. And in quadrant 1 or quadrant 2 or quadrant 3, quadrant 4, all the hypotenuse has to be positive. And that's it. End of explanation. Is it right? But I have to tell you that I myself not sure if that's a good reason. No, I don't think that's a good reason. You see? Okay.
Yeah, that makes sense.
Yeah, that's I don't think that's a good reason, because I can easily use question, for example, part number 39, and why they still use absolute sign there, you know, and so on and so forth. Okay, so I don't know why they use absolute sign, but in my work, I don't have absolute sign for my u. Okay, let's take a break. We come back at 9:11. Not a good number, but yeah, 10 minutes from now is 9:11. Okay, so the purpose of 7.4 is to integrate rational functions. What is rational functions? Rational function is a polynomial divided by a polynomial. Okay, now in our section here, we will focus on integrating proper rational functions. Now, what is proper rational functions? That's when the degree on the top is strictly less than the degree at the bottom. Okay, that's proper rational functions. For example, x over x squared plus 1. Okay, that's rational, proper rational functions. This is proper. Okay, improper if the degree on the top is greater or equal to the degree at the bottom. Let's say if I have 2x squared plus x plus 3 over x squared plus 1. Now, the reason we don't need to deal with improper rational functions, because we can divide this, and get a polynomial plus a proper one. Okay, as long as the degree on the top is equal or greater than the degree at the bottom, then we can always convert that into polynomial plus a proper rational function. Just like think of that as a improper fraction, you know, improper fraction, let's say, for example, 15 over 7. We can always divide that and get an integer plus a proper fraction. You see? Okay, so suppose I use that improper fraction. Suppose I have, for example, I have that 2x squared plus x plus 3 over x squared plus 1. Then I can divide that. 2x squared plus x plus 3 over x squared plus 1. That's 2 times, so I get 2x squared plus 2, and then when I subtract, I get x plus 1. So this is equal to 2 plus x plus 1 over x squared plus 1. Do you see that? Now, this is the polynomial, and this is the proper rational function. Okay, that's why then in this whole section, you don't really see us integrating improper rational functions. Okay, we will focus with the one where the numerator has degree less than the degree of the denominator. Okay, that's one. Second, we will use partial fraction decomposition. Partial fraction decomposition, which I supposed to teach in pre-calculus class. So if you took my pre-calculus, I supposed to teach this, but I never have a chance. I never have a chance to teach partial fraction decomposition. I know some instructor teaching pre-calculus class at West LA College had some chance to talk about partial fraction decomposition. Now, what is partial fraction decomposition? Basically, we will decompose a fraction or a rational function into the sum of simpler fractions. Okay, now it turns out that there are 4 types of partial fraction decomposition. Scroll down. Okay, there are 4 types of partial fraction decomposition. let me show you first a simple case. What is partial fraction decomposition? Let's say something we did in algebra 1. For example, if I have 3 over x plus 2 plus 4 over x minus, let's say, x minus 5. How do you add these two fractions? You do the LCD. This is 3 times x minus 5, and this is 4 times x plus 2. Am I okay? Now then, the reason I have LCD so that I can put them together under one fraction. So I get 3x minus 15 plus 4x plus 8. This is 7x minus 7 over x plus 2, x minus 5. Is it okay so far? Now, so what we did here, basically what we did here is we get 3 over x plus 2 plus 4 over x minus 5 equals to 7x minus 7 over x plus 2, x minus 5. That's when we add those rational functions. Now, partial fraction decomposition is going backward. Partial fraction decomposition is going backward. Now, let's see what happened. Let's see how the good thing about this. Suppose then later on, if I need to integrate 7x minus 7 over x plus 2, x minus 5 dx, then I decompose that integrand into 3 over x plus 2 plus 4 over x minus 5 dx. Is it right? Okay, now the procedure to come from here to here is partial fraction decomposition. Okay, you will see that we will focus our effort a lot in decomposing. But once we are able to decompose that, notice that the integral after this is Mickey Mouse. This is 3 natural log of absolute x plus 2 plus 4 natural log of absolute x minus 5 plus constant. Okay, but how to go from 7x minus x over x squared minus 3x minus 10 to 3 over x plus 2 plus 4 over x minus 5. Okay, that's where we learn partial fraction decomposition. Now, there are four types of partial fraction decomposition. Now, if you already watched my lecture video, that will be great. If not, I assume you don't watch it yet. Okay, so I try to focus more on the foundational theoretical foundation instead of going to the integral right away. Okay, now the first type is, let me call that 1. The first type is the type with distinct factors. The denominator qx is product of distinct linear factors. what's that terms? For example, the one we had just right above this. For example, when we factor that x squared minus 3x minus 10, when we factor that, we have product of linear factors without repetition. Without repetition, you see the multiplicity is 1, multiplicity of 1. Remember polynomial in your pre-calculus? It's all multiplicity of 1, and the base is linear form, like x plus something or mx plus something, mx plus b. Okay, so let's say I have 2x squared minus 5x plus 2. This is 2x minus 1, x minus 2. You see, the exponent are all multiplicity of 1, exponent of 1. And the base is in linear form, mx plus b. Okay, now let's see the second type. The second type is when the denominator is product of linear factors with repetition. For example, if we have x squared plus 6x plus 9, that's x plus 3 squared. So we have repetition there. You see? Or x squared plus 3, I'm sorry, x cubed plus 3x squared plus 9x plus 27. That's x plus 3 squared. I'm sorry, x plus 3 cubed. Will that be, hold on. I think it should be, my bad, 3 choose 0, 3 choose 1, 3. Should be 9 here. That should be 27 here. Would that be right? You know what? Let me try. So x cubed 6 plus 3. That's 9. That's right. And then 9 plus 18, 27. Yeah, that's right. Basically, then we have repetition. Like the exponent is repeated. Okay. Now, the third one, qx is product of irreducible, the product of irreducible quadratic factor. No repetition. For example, if it looks like, let's say, x squared plus 2 times 2x minus 3, you see that this is irreducible. We cannot factor it further. Okay, we cannot factor it further. Let's say another one, x squared plus 3x plus 3. Okay, that's not factorable. Now, however, the exponent is still exponent 1. Right? That's how we say no repetition. Case number 4, the last one. The denominator contains irreducible quadratic factors with repetition. Okay, so let's say, for example, if the denominator has x squared plus 2 to the power of 3, or x squared plus, let's say, 4x plus 6 to the power of 2, like that. It's not factorable, yet the exponent is not 1. Okay, now it turns out all polynomials on the denominator can be factorized to be one of these 4 types or the combination of one of these 4 types. Okay, now what we will learn right now in the next 20 minutes is how to decompose type 1. Okay, type 1 QX QX is product of, the denominator is product of distinct linear factors. You will see we basically learn about pattern. Okay, let's see. Suppose, for example, let's start with example 1. Suppose, for example, we have number 1a. So I do problems from our book. Maybe 2a. Number 2a. Number 2a. How do we decompose x over x squared plus x minus 2? Factor it first. This is x over x plus 2, x minus 1. So far, is it okay? So the assumption is you know how to do factoring, which something you learned at least 2 years ago. Okay, at least from 2 years ago. Now, here's the thing. If the denominator consists of distinct linear factors, then you will break it up into something over the first linear factor plus something over the next linear factor. Okay. Now then the numerator you use has to be 1 degree less than the denominator. So for example, the denominator here is degree 1, right? X plus 2 has degree 1. So the numerator has to be degree 0. In other words, that's just a constant. Okay, the denominator x minus 1 is degree 1. So the numerator has to be degree 0, or it's just a constant. What we are going to do is to find this A and B.
Does it matter which one goes first, or like
Doesn't
which one's
matter.
A?
It doesn't matter.
Oh,
Doesn't
okay.
matter. Yeah, so your A and my A may be different, but when we write it out later on, replacing the A with the actual number, then we will come up to be the same. Okay. Now, there are two methods. There are two methods. Two methods to solve for the A and B. Basically, it's to solve for this partial fraction decomposition. The first method is called grouping method. Not factorization by grouping, it's just grouping. And the second method is special value method. What is grouping method? Here's the way. You know what? Let me move this a little bit to the right. At first, a lot of students like special value method, but I need to warn you ahead that both of these has its own strong point. Okay, grouping method has its own good thing. Special value method has its own good thing. So, suppose I use grouping method. What is grouping method, Thomas? Let's see. Suppose I need to solve for A and I need to solve for B, right? So I will multiply by the LCD. When I multiply by the LCD, I will get X on the left-hand side. On the right-hand side, I will get A times X minus 1 plus B times X plus 2. Now I distribute, combine like terms, so I get AX minus A plus BX plus 2B. The X terms, I put them together, so that's A plus B times X. And then for the constant, I get negative A plus 2B. Can you follow me? The X terms, I combine AX plus BX, right? And then the constant, negative A plus 2B. Is it okay? Now, on the other hand, when you look at the left-hand side, you see the X term. What is the coefficient of X term? On the left-hand side, the coefficient of X term is 1. The coefficient of X term on the right-hand side is A plus B. Any questions so far? No question. Okay.
What do you mean? I'm sorry. Repeat that again.
I mean, if you look at the X term on the left-hand side, that's only X, right?
Mm-hmm.
The coefficient is 1.
Right.
Now, on the right-hand side, what is the coefficient of X?
Oh, it's 1.
The coefficient of X on the right-hand side is A plus B. So A plus B must be equal to 1.
1?
Yeah, on the left-hand side, the term X has coefficient 1, right? On the right-hand side, the term X has coefficient A plus B.
Oh, okay.
So the coefficient must be the same. Now the constant part, the left-hand side is 0, on the right-hand side is negative A plus 2B. Now then you solve this system of equation. Solve the system of equation. Like in this case, one thing you can do, you add both sides. So you get 1 equals to 3b, b equals to 1/3. And then if b equals to 1/3, you plug that in. 1 equals to a plus 1/3, then the a must be 2/3. Therefore, x over x squared plus x minus 2 is equal to 2/3 of x plus 1. What is my a correspond to? A plus 2. A correspond to a plus 2 at the bottom. Plus 1/3 x minus 1. Now the thing is, grouping method may give us a lot of variables instead of only 2 variables, a and b here. You may end up with a, b, c, d, e, f, g. It grows really fast, really big. On the other hand, special value method has its own weakness. So do not think that special value method is better. No, it has its own weakness. Okay, I will show you the weakness actually, I think next week. No, no, on Friday. On what Friday? On Wednesday, I mean. Now we have x over x plus 2, x minus 1 equals to a over x plus 2 plus b over x minus 1. Just like the first step, the first method, I multiply by the LCD. So I get x equals to a times a minus 1 plus b times x plus 2. But I do not distribute this. I will not distribute this in my next step. I will use special value method. What is special value method? Choose a certain x such that you can eliminate a term fast. For example, let me choose x equals to 1. Why you choose x equals to 1? Because when x equals to 1, this becomes 0. Are you with me? Okay, so when x equals to 1, I will get 1 equals to a times 1 minus 1 plus b times 1 plus 2. But you know the reason you choose x equals to 1 so that this term cancels, right? Okay, so basically we have 1 equals to 3b, so b equals to 1/3. Now choose another x that kills the other term. What x supposed to be such that this becomes 0?
Maybe -2.
-2. So I will choose x equals to -2. So -2 equals to a times -2 minus 1 plus b times -2 plus 2. Of course, you don't need to show your work this way. You can just go ahead. Okay, -2 equals -3a, right? So -2 equals to -3a plus 0. So a equals to 2/3. So x over x squared plus x minus 2, actually, yeah, equals to 2/3 over x plus 2 plus 1/3 x minus 1. Is that okay? Now, I don't remember which question I did in my lecture, but let me, to make it safe, let me do odd number. Let's say number 9 in our textbook. How do we apply that later on to integral? Integral of 5x plus 1 over 2x plus 1 x minus 1 dx. They already factor it for us, so I will start the process of partial fraction decomposition. 5x plus 1 over 2x plus 1 x minus 1. This is equal to something over 2x plus 1 plus something over x minus 1. The numerator has to be 1 degree less.
Thomas, when would you like what would you recommend, like when you look at an equation, to go either with grouping or the special value?
We don't know. Okay,
Do you just try both, or you just try one and see if that one is
both of them will work. Both of them will work.
okay.
Now, I can tell you now when to use what, but I think I'd rather you practice so that you know why one, in what situation do what, in what situation do what. Because even until now, I have not seen any professor, not only any students, I have not seen any professors know for sure when to do what.
I see. Okay.
Okay, so including me,
Are you gonna show both the grouping and the special value for this one?
I can tell you that for type 1, use that substitution, the special value always faster.
Okay.
Yeah, for type 1, the special value always faster. For type 2, it's the mixture. Type 3 is the mixture. Type 4 is the mixture. Okay, now then I will try to solve for A and B, multiply by the LCD. If I multiply by the LCD, I will get 5x plus 1 equals to A times x minus 1 plus B times 2x plus 1. Now then, let me choose x equals to 1. When x equals to 1, this is 5 plus 1 equals to, this is 0 plus 3b. Is it right? When x equals to 1, so 2x plus 1 becomes 3. So 6 equals to 3b, b equals to 2. Go on. What is the other special value? Negative 1/2, right? 5 times negative 1/2 plus 1 equals to A times negative 1/2 minus 1 plus 0. That's negative 5/2 plus 2 over 2 equals to negative 3/2 A. Negative 3/2 equals to negative 3/2 A. Oh, then A must be 1. So, so 5x plus 1 over 2x plus 1 times x minus 1 is equal to A over A plus 1. That's what my A corresponds to, right? So I basically replace my A and my B now. Okay, I replace my A and my B now. So I get A equals to 1 and my B is 2. That's 2 over x minus 1. But we are not done yet, because the question is not to decompose this. The question is to integrate that. Okay, now I go back to my integral. Integral of 5x plus 1 over 2x plus 1 x minus 1 dx. That's equals to integral of 1 over 2x plus 1 plus 2 over x minus 1 dx. So you already decomposed that. Now you can integrate that. This is 1/2 natural log of absolute 2x plus 1 plus 2 times natural log of x minus 1. Don't forget plus constant.
Wait, why is the first one 1/2?
Because I integrate that. You can do substitution. U equals to 2x plus 1. So
Oh.
right?
Yeah. Sorry.
Okay. So once we finish with the composition, then the next step is actually just to integrate. Okay, I have 1 minute left, but let me do one more problem. Okay, let me do one more problem. Let's say number 11. But I will take off the boundary. So basically, I will omit the boundary so that we can focus more on the integration by part. I'm sorry, partial fraction decomposition. That's 2 over 2x squared plus 3x plus 1. So again, I will omit this so that we focus only on the partial fraction decomposition. So partial fraction decomposition of 2 over 2x squared plus 3x plus 1. That's 2 over, you need to know how to factor them, 2x plus 1, x plus 1. Which will give us a over 2x plus 1 plus b over x plus 1. Multiply by the LCD. Then I get 2 equals to a times x plus 1 plus b times 2x plus 1. Then I choose my special numbers, -1 for example, will be 0. So my b is -2. Okay. Now, actually, from here, if you want to suddenly switch to, well, if b is -2, then look at the group, right? This is 2 equals to ax plus a plus 2bx plus b. Okay, and then you see the group 2 equals to a plus -2. So a must be a must be 4. So in other words, that special value method is not, that's just a style, but it doesn't have to be like you have to do it that way from the beginning to the end. You can mix them. You can mix them. Okay, you can mix them. So let me do it here. So this is 2 equals to, for the constant term, 2 equals to a plus b, but we know the b is -2. So the a must be 4. Right? Okay. Now, if you insist, you know what, Thomas, I like that special value method. Okay, fine. So x, the other special value method, the other special value is x equals to -1/2, right? So the left-hand side is already 2a times -1/2 plus 1 plus 0. 2 equals to 1/2 a, so a equals to 4. Now, if you ask me this question, Thomas, how do you know I should do this or do that? Then I go back to you. When you try to do that, what do you have in your mind? Okay, then do that first. Because to be honest with you, if you keep on thinking what method is better, you better spend that time to actually do it using one of the methods that first come to your mind first. Okay, now, but once we are done with this partial fraction decomposition, let's summarize that. So 2 over 2x squared plus 3x plus 1 is equal to 4 over 2x plus 1 plus negative 2 over x plus 1. Therefore, the integral is equal to integral 4 over 2x plus 1 minus 2 over x plus 1 dx. Then this is 4 over 2 natural log of 2x plus 1 minus 2 natural log of x plus 1 plus constant. That's 2 natural log of 2x plus 1 minus 2 natural log of x plus 1 plus constant. See, the integral part tends to be on the easy side. The partial fraction decomposition is the one you need to practice. Okay, now on Wednesday, I will go over type 2, type 3, and type 4. On Wednesday, I will go over type 2, type 3, and type 4. This is where I will stop. See you on Wednesday.